hopefully you have all had a great recovery from the exam or whatever, and we are ready to do the next phase of the course, which is we're going to cover a bunch of different topics, but we begin with algorithms. We'll talk about sorting algorithm today, and thank you. And we'll talk about, we'll cover sorting algorithms today, at least some subset of them, and they're all interesting from the point of view of the MPI learning and parallel structure and algorithms and so on. Okay, so the problem we are looking at, I think I described the problem last time, that the data is spread across all processors, and we want it sorted. That means we want data on processor I to be smaller than any data item on I to be smaller than any item on I plus 1, and within each processor it should be sorted. I definitely remember stating this problem a week or so ago, right? But we didn't get into that, did we? I don't think we did the algorithms themselves. So I was just introducing the problem to be solved next time. So and so the input, you cannot assume that the data is all on one processor because that will be non-scalable. We are interested in scalable algorithms. The practical situations in parallel computing that arise involve data that's spread across processors, and so that's what we're going to assume. And so right, so each record has a key and some data of b bytes. We'll assume key is 64-bit. We'll later on maybe discuss what's involved if the key were to be something long, like a name or string of some sort. So at the end, what we want is we want processor. We want the same keys and records to exist. No records should have disappeared. No random magic records have been added. The second thing is every processor should have roughly equal number of records. And then third thing is that they need to be sorted in the way that we defined. Approximately N over P is good enough because making it exactly is quantization-wise impossible. Maybe the total number of keys is not divisible by the total number of processors. So at least plus minus 1, there will be a difference. But also, the reason that we want them equally distributed is so that is for the sake of load balance of the subsequent algorithm that we're going to run on them. And so for it to be 1% off is probably acceptable. And because 1% load imbalance you'll get through other means, just through sheer noise of some sort, variation in various computations. And so maybe a couple percent off from the ideal size of N over P is what we should be willing to accept. And if we do, the question becomes how can that relaxation be leveraged to optimize the execution of your algorithm, right? And those are some of the considerations to keep in mind as we look at different algorithms. So one could do a comparison-based sort, or one can do something that's not just confined to comparison. What is not just confined to comparison? A radix sort, right? And so when you look inside of a key, does everyone remember radix sort from their data structures? Okay, we're going to study that, but this is the sorting method where you look at a 64-bit key, take the 16 bits of it, and say, okay, we'll just sort them based on these 16 bits. We'll just put them in different bins. Well, we'll look at if you haven't studied it, we'll just spend a little bit more time when we come to that algorithm. So there are some algorithms that can be faster because they can look inside the structure of the key. Radix sort being one example. But the other algorithms where we say, well, comparison is a more general operation. So all that you're allowed to do is to the keys is compare them, smaller, larger, or equal, and base your sorting on that. And in that category, there is a well-known limit on how fast you can do it sequentially, which is that you need n log n comparisons. All right. So you cannot have an algorithm that will do it faster than n log n in the worst case. Okay? So you can get lucky and do something in order n, just find everything is sorted and call it done. But if the data is randomly permuted, in the worst case, there is no way you can get anything better than n log n. Because there are, after all, n factorial possible permutations of those n things. And to figure out which one of those n factorial you got, and you have a comparison that says smaller or larger, that just separates possibilities by equal halves in the best case. So log of n factorial to the base 2, well, that turns out to be n log n with some Stirling's approximation and so on. But that's where we have that limit. And so how do you sort, how do you do a comparison-based sorting in parallel? And how can you do some other sorting algorithms in parallel, right? So where is sorting useful? Well, it occurs in various places. In particular, the place where I've encountered it most is our cosmology collaboration. We have n particles spread across processors. And one way of partitioning the particles to processor that preserves locality in some way, that is, keeps nearby particles on the same processor. By the way, well, the answer is stating here, but we have a bunch of particles. They have coordinates. You want nearby particles on the same processor. How can you do that through sorting, right? And the idea is, and it's a cute trick. You take the x coordinate, y coordinate, and z coordinate. Maybe take only 21 bits of the most significant bits, or imagine them to be in a box of size 0 to 1, so you can normalize them. So you don't have an issue with the mantissa, with the exponent being different. So as long as the coordinates are with the same exponent, think of the coordinate, x coordinate, take the most significant bit of it. If it is 1, that tells you that the data is in the second half of the x space, right? If it's 0, it tells you it is in the first half, right? And then you take the y coordinate, and it takes its most significant bit. That tells you whether it is in the upper half or the lower half of the overall space. Remember, you have already normalized it so that the numbers are between 0 and 1, and so with the same exponent. And so depending on the first bits, you can actually classify it here or here. Now, if you take the x coordinate first bit, y coordinates first bit, z coordinates first bit, then x coordinates second bit, second y, second z, and interleave them like that in that fashion, what are you getting? You're getting an octet decomposition of the particles, right? You're getting basically, if it is 0, 0, 1, that means of the 8 octants, I'm in that octant. All the particles that are in that octant will have their first 3 bits be 0, 0, 1, right? And so with that trick, recursively continued, what you get is anyone who has the similar coordinates as that 64-bit number, 63-bit number will be very tightly in a very tight bit of space, 1 millionth of the along each dimension, because at 20 bits, 1 millionth, 1 divided by 2 million actually along each axis. And in cosmology is famous for, or infamous for, having particles spread in a highly varied density. So even though that's a million cube number of cells we are specifying with the 63 bits, you will have some of them absolutely not populated, and others will be heavily populated. So the density variations can be very high in cosmology simulations, just because you look up in the sky and see where the stars are, and then see where the galaxies are and how much empty space is there between them, right? And that tells you that the density variations are going to be very heavy. So with that trick, you now have these boxes, and then if you sort them, just considering that 63-bit number to be just a 63-bit number, put a 0 at the end or something, and then 64-bit number, if you sort them, nearby particles are going to be nearby in that linear order. So that's the intuition behind it. This is called a Peano-Hilbert space-filling curve. And there are other situations like that. So then if you distribute the particles that way, then each processor has a set of particles that are all nearby each other, and various algorithms for calculating gravity will work better when most of the nearby particles are on the same processor. So I think we'll skip other examples, and we'll start looking at 2 or 3 different algorithms, maybe 4. First algorithm is a Radix Charge. So since many of you said, though you don't remember it, it will come back to you, believe me. Here is the way we do. Let me give you first a small example. Sorting arbitrary data with all kinds of 64-bit keys is hard. But what if I give every one of you a serial number? So you know you are a student with serial number 29 in the class. You know you are a serial number 45 or something like that, right? And they are all contiguous. If there are 70 students in the class, the numbers go from 1, okay, fine, 0 to 69. And now I have a jumbled up list of students and their scores in the exam, and I want to sort them. Will it take n log n time? I can do much faster than that, right? What would I do? Or suppose I have 1 million people and everyone has a distinct serial number, right? Distinct serial number that's contiguous. So their serial numbers go from 0 to 1 million minus 1. Okay. What can I do to sort their scores? Sort them by scores. Will it take n log n time, or can I do it faster than that? Yes? Don't even have to do that. You're going to need an array of size 1 million anyways. The index of the array is the place where each record goes. So I take the record of student number 45, score whatever, and I just put that record in the 45th location of the array, right? So the index acts as the place that you just kind of, in constant time, you just put it in the right place and you're done. And you're able to do that because they were all contiguous. Now, why? I cannot use that idea when things are not contiguous. I can use it maybe, but there'll be holes in the array. And if the number of holes in the array are large, if I have 10 million possible numbers and I have 1 million people, maybe that's a 1 to 10. That's already kind of bad, because then to collapse them at the end, I will have to traverse all those 10 million things. But maybe not so bad. It's still kind of, it's like comparable to your n log n algorithm. If I have social security numbers, which are how many digits? 9 digits. So 9 digits is 10 to the power 9, which is a billion. Billion only? Am I wrong? Yep. 10 to the power 9. That's how many things there are. But there are, in a particular database, you might have everyone in the US, and that's still 250 million, right? 325 million, whatever the number is now. That's still much less than the possible number of social security numbers. That thing is called the namespace. So the namespace is larger than the size of the array, right? And so when the namespace is very large, if you have 64-bit things, 64-bit coordinates for these particles, and there are only a few billion particles. A few billion particles is still much, much smaller than the namespace represented by 64 bits, which is 2 to the power 64. 2 to the, what is that approximately? Someone quickly? As powers of 10? 2 to the power 10 is 10 to the power 3. That's the thing to remember. 2 to the power 10, 1024, is 10 to the power 3. And so you have, how many 2 to the power 10s are there in 64? 6, right? And there are 4 left. Forget them for now. And so 6 2 to the 10s, which means 3 10 to the, okay, I confused myself here already. So anyways, I was just going to tell you it can be done very easily, but 2 to the power 60 is 2 to the power 10 to the power 6, right? Which is 1000, which is 10 to the power 3 times 6. Yeah, I was right. 10 to the power 18. So that will be 10 to the power 18 already, and then you have this 2 to the power 4 on top of it, because this is actually 63, not 64. But so that will be another power of 10 almost. So that's a huge namespace you have there. The number of particles you have is going to be only about 10 to the power 9 or something like that, maybe 10 to the power 10. That's a huge difference. There is no way this array method is going to work for us, right? But an idea that's close, that kind of draws upon that idea of looking inside the key, which is what we did, right? We just looked at the key and said that's where it goes. We can actually do it by their by the digits. And so that's the idea of, let's see if I have the idea for, let me see. So let me show you the animation for numbers using the decimal formulation. Decimal formulation is absolutely of no use on a computer because 10 is not a round number. Well, only in the appropriate representation. But 10 is, so you use typically powers of 2 so that it's much easier to mask off bits to extract portions of it. So here we're going to just use digits because it's much easier for us to work with. And the basic idea is first you sort, put them in 10 buckets. Are there 10, 3, 5, 7, 9, 10? Yes, the 10 buckets. Put these keys in the 10 buckets based on their, which one? Least significant digit or most significant digit? Yeah? No. So that's a trap. I just said that for you. So it turns out you do it from the least significant, and you will see why. Because in the end, you want them by the most significant digit. And then within that, you want them by least. So the next phase, we'll do them by more significant digit, okay? So sorry, I intentionally laid that trap for you there. So all right, so you take this, say 23, that's 3. Where does it go? This is 0, 1, 2, 3. So it goes there. And you keep them in order in which they arrive. In the beginning, it doesn't matter. In the next phase, it will matter. And then 18, where should it go? Into that one here, right? Okay, because it's 8th bucket. Okay. 45, 5, that goes in one, that should be about here, yes? Okay. 92, that should go there, 0, 1, 2. 15, that's 5, that goes on top of that thing there. 12 goes 2 again, it goes here. And 48, that goes here. A carefully chosen thing so that there are at least some buckets with 2 things in there. All right, now what you do is you take things in this order. From originally, we are just, this is sequential algorithm we're talking about. Originally, we're just taking the keys from left to right. Now also you take them from left to right, but going bucket by bucket. So you pick things from the early, a bucket which has a lesser significant, smaller, lesser significant digit than the one that has larger, lesser significant digit, right? The least significant digits here. So you do 12 first and then 15 because 2 is smaller than 5, right? That's the point. So you pick that 12, and where do you go now? Now you again make 10 sets of buckets, and 12, this time you base it on the next digit, which is, in this case, in 2-digit example, that's the most significant digit. And so that goes by 1 into this bucket here. Whoa, okay. So, all right, that 12 goes there. That's just same thing drawn again. 92, then that's 9. Now we're looking at the second digit, right? Second most significant digit here. And that goes into the last one then, right? And now 23, 2. And so that goes into that one there. Then comes 15. It goes based on 1. It goes here. Now you see why we pick them in that order. Because now 12 is before 15. So if you pick them up like this, right, in the 5-4 order on each thing, you just pick them like that, then you're going to get a sorted order. And so 45, that's 4, that goes in there. 48, that's also 4, that goes on top of that, so it's larger than that. And then 18 goes down there, it's larger than those, and then we are done. And now we just collect them from here, 12, 15, 18, 23, 45, 48, 92. Wow, we'll actually have to say nothing here, nothing here, nothing here, nothing here, then 92. There is that part of the complexity. But usually the number of buckets is much, much smaller than the number of keys. So there will be several keys in each bucket. All right? So this is the idea for the Radix sort. Right? Now, a couple of things to note. One is that it is not a comparison-based sort. You did not compare one key to the other. But it does involve looking inside of the key. You broke the key down into its digits. Right, and then looked at the digit for most significant digit and the least significant digit and so on. The second thing, well, that's, and then of course when you do it on a computer program, you will, instead of digit, you will use a base 16 or some such power of 2 base, right? And a reasonable base to use could be something large. Like in a 64-bit key, you might want to use 2 to the power 16 as a base. Not 16, 2 to the power 16. That's like 65K. So if you so then there's only 4 digits in the whole 64-bit number, but each digit is pretty big, and the number of buckets is very large, 2 to the power 16, which is 65,000 buckets. Okay, but that's still fine because you're sorting billions of keys or millions of keys, and so in each one there will be several keys typically. So is that everyone with me so far? So that's how we want to do it. Now the question is, how do we do this in parallel? Keys are already distributed to processors, so you're not centrally going through them in any order. Now you want to focus on the least significant 16 bits. So you mask out the least significant 16 bits. That's easy enough. And now you have a number between 0 and 64K. What do you do with that number? You want to put that number in the key into that bucket, right? Where is that bucket? On my processor? On someone else's processor? That's one question. Okay. And the second thing is, what do you do afterwards, after you have gotten all the counts? What's the answer to where should we keep the buckets? With 16 bits, the concrete example, with that concrete example, where should we keep the bucket? Oh, sorry, one first separation. We would like to know, when we do this with processors, we want to know what is the size of each bucket? Where should each data item go at the end of this first phase? Right? You have this phase here. Now, in this phase, they are unevenly distributed, right? Whichever way you actually do it, suppose you actually move the data to the processors, that may not be the best thing to do, but if you were to do it, just notice that at the end of this phase, these numbers are distributed across all processors. These buckets are distributed across all processors, which means all the numbers in the buckets are. We want them to be even in that phase too. It's not adequate to have the load balanced at the end of the sorting. It needs to be balanced in between too. Otherwise, you're going to have your algorithm itself might have an issue with performance, right? And so, because you'll be waiting for one of the processors to finish its sets of numbers. So a thing that suggests itself is not to move the particles, separate out the two steps. How many particles go into each bucket? Just count them. You first want to just count and then move them to the correct bucket. Then figure out which processor those buckets should live on, and then so that the load is balanced, and then move data to the correct bucket. If there are 65,000 buckets, then the data moved, if there are 1,000 processors, if the data were uniform, every processor will get 64.5 buckets, and then you can move the data to the correct place. But if they're non-uniform, some processors, initial processor might have 201, then another 201, then only 20 buckets here because those happen to contain lots of numbers and so on. So they can be uneven. We need to figure out how many buckets, which buckets to assign to which processor, right? So the first things first, let's just say count. How can we say how many things at the end of this orange step will be there in each bucket? We just want a count for size for each bucket afterwards without actually doing any data movement across processors. We want to know how many keys belong to each bucket. On my processor, I have some subset of data. What can I do? I can just process my data. I'm not going to move my data to another processor, so I can process my data and do essentially this algorithm on my data, except instead of moving it there, I just increment a count, right? So for every bucket, I have a count on my processor. So my keys, 73 of them go onto this bucket, 20 go onto this bucket, 500 go onto that bucket, and so on. So I have a count for how many of my keys go into each one of the buckets. Okay? but I need to know how many keys are there globally in that bucket 0 and bucket 1 and bucket 2. Yes?
So would it be better to like do like a broadcast to everybody saying like an array of like I have this many bucket 1, this many bucket 2, this many bucket 3, or would it be more efficient to do like a reduce for each one of the buckets?
Yeah, you tell me. I mean, for a,
Probably the broadcast because reduce would require more envelopes.
in fact, what are you going to broadcast?
I was thinking an array. So like the first index is how many I'm going to put in bucket 1. The second index is how many I'm going to put in bucket 2.
But then, who is broadcasting that?
Everybody. So sorry, I guess that's
It's an all-to-all. Yeah, all-to-all is more expensive than a reduction, right? And all-to-all requires essentially, I mean, we'll look at the collective algorithms later on, but it's very easy to see that, yes? You're just pushing the problem to the charm runtime, all right? The charm runtime has to do it. So in this class, there is no escape. You have to do the algorithm yourself, all right? But otherwise, you're right that you can just let the system balance them. But sorting, you don't get much of a second chance, right? So system can do a measurement-based load balancing in charm, but by the time it does the measurement, it's already too late. You're working. So if you have lots of steps afterwards, you could do that. But otherwise, if your objective is to right away balance the load, then you don't have the luxury of measurement-based load balancing. So let's say we just add up all the counts. So now what you have is on my processor, I have an array of what? Single numbers, right? Array of numbers saying count for bucket I on my processor is this much. In the global scheme of things, this is how many I will contribute to this bucket. If you add all those numbers across all processors, which is what a reduction allows you to do, you will get a global total, and you can do an all reduce so that everyone has that total that says that I know now that bucket 3, how many keys are there in bucket I for every I globally, right? Now, does that tell me where should I send my keys that belong to bucket 73? It does, but indirectly, right? I have an array of counts. Basically, I have an array of counts that says count sub 0, count sub 1. This is our global counts. And I also can do in a separate reduction if I want, or I can just sum up all of those, and that will be the total number of keys, which I know is n, right? So I know how many per processor there need to be, n over p. So I can just start going from here and saying, okay, I'll take that for 0, I'll take that for 0, add them up until they become larger than n over p. Or stop just before they become larger. Well, you could go until they become larger than n over p, and then you say, that's mine, that's for 0, not mine, that's for 0. And then start the count here again, add up until it becomes less than n over p again. Well, you could pick a threshold so that it's not n over p, otherwise the last guy will get very little. So you could pick some kind of a simplification there, but let's just say n over p. Everyone has to execute exactly the same algorithm, same scheme, so that everyone's idea of which buckets belong to which processor is the same. And so you just say, okay, I now have an array here that says processor 0 owns bucket 0 to bucket 17, processor 1 owns bucket 18 to bucket 23, and so on, right? So I can have an array that tells me processor-wise which buckets belong to which processor. And now I can take my go through my keys, put them in a vector that's going to bucket I, and send those keys that belong to a particular bucket to that processor, right? In that order, because it has to process them in the left to right order. So I will send them an array of buckets where each bucket is an array of values, which is not hard to, but you'll have to think about how to do that in MPI or in Charm for that matter. You're sending two arrays. One is the array of counts, and the other one is an array of actual data for each bucket, right? And you send it to that process saying, hey, here are your buckets and what values I have for you. And so you could send the key as well as data, or just send the key and collect the data later on. I will leave that part of it out of this discussion. Let's just focus on keys. So now you completed your step 1. right? So still not quite complete. You have to do the receives corresponding to that. How many receives is everyone going to do? That's p minus 1. Everyone else is sending them some data. Even if it is 0 data, they have to send a message, because otherwise, how am I going to know that you don't have anything for me? So I'll forever wait for that. So instead, everyone sends a piece of data to everyone else. Now this is an all-to-all personalized communication, but let's not get into that. Let's just say you send a point-to-point message to everyone saying, this is your data, this is your data, this is your data. All right? So that's a data permutation step. And now you're to this point such that one processor has this, another processor has this, another processor has this data, right? So that's step 1 completed. And now you repeat that step. You go through the keys in the order left to right and within each vector in the correct order, and then decide which bucket it needs to go to, increment the counts, do a reduction over the counts, get the processor number to which, get the distribution of buckets to the processors, and send your new buckets to data to the new buckets wherever they belong in another all-to-all operation. Because even though you own just this, your data will go all over the place because it's now based on the second digit, right? The more significant digit. So it will go all over the place again, and so it's again an all-to-all operation. So is the algorithm clear then? Let me see if I can put it in words better. Sort data based on the least significant 16 bits, redistributed data keeping the load balance, and repeat the steps again. Skip the animation. Okay. So, okay, any question about this? Okay. Now, second algorithm is, this algorithm is actually, yeah, this first algorithm was at least the earliest one that I know of was done by Kurt Thierling in 1993, and coincidentally in 1993, and Kurt Thierling was a student in my class here. I used to teach algorithms that time, and he joined connection machines. And then here in my research group, we did something called a histogram sort around the same time, and it appeared in the 2 different conferences. So what is the idea of histogramming? Histogramming is a comparison-based sort. Oh, let me tell you one other small trick that they did. It's a really nice trick in this algorithm. So if you look at the step that you have to do, the very first step, you're looping over all your keys. If it is in the second phase, you're still looping over all your keys and incrementing the count for each one of the 65,000 buckets, right? What do? You take the key, its ith digit, whatever digit you are on, extract those 16 bits, and those 16 bits tell you a bucket number, and you go increment the counter for that bucket number. That's all, right? That's the first pass. Then in the second pass, you're sending the data off to someone. But that counting part, they had a problem, which is that they wanted to improve the cache performance of that first phase, and it's pretty bad because what happens is every digit, as you're looping through your keys, that digit may be anywhere, right? That digit may point to any one of the keys. So it is just like histogramming. Your performance cache behavior is pretty bad in that you pick a key, extract the bits, you go there. You pick the next key, extract those bits, and increment the count of this one here. All over this space of buckets, you go randomly. And so you will get a cache miss pretty much on every access to the bucket array. So, well, except this is only 65K. In the particular cache they had was, I believe, 32K, right, or something like that, some smaller number. So what this did is they said, we're going to have, and the count, how big is the count need to be? Count can be anything, right? So they said, well, we're going to make the count to be only an 8-bit number, the count that you're making for each thing. So now that's just 1 byte, and so 65K buckets, so 65 kilobytes. That actually fit. So I forget now what the numbers were. Maybe the size was 65 kilobytes. You just pick that size, and so what? So what happens when you overflow the count? Well, when you overflow, you go to the real array. and increment its count correctly and reset your count to 0, right? So you are just kind of keeping, so 1 out of 256 operations will go into this bigger data structure. Other operations are into this compact data structure where you're incrementing each count. Yes?
Would it be beneficial to use OMP to drive that counting
Today,
process and leave those as atomic?
yes. Yes. So in the original 93 time frame, 1993, there was no multi-core nodes. They were either multi-core supercomputers or they were parallel computers made up of single-core nodes. But today, you would do, it will be an interesting exercise to see if we should do a separate OpenMP inside or do a separate ranks within each MPI ranks within each node. But you will use something like that. And I think the deciding factor will be this histogramming, common histogram or separate histograms, then locally add them up. That might decide which one wins. Okay. So that was a cute little trick that gave them pretty good performance, although the communication dominates where you have to do all-to-all communication. Then the interesting thing is how many times you distribute the data, permute the data here? 4 times. Every phase you have to send the data, you do all the counts, you do the reductions, maybe the reductions are pretty fast, but then you have to take all the keys, and they typically had like 8 million keys per core or something like that. And you have to send all those 8 million out to someplace, some different processors. So that permutation is an expensive step, and you're doing 4 of those. The idea of a histogramming sort, it doesn't look inside of the key, it is only comparison based. And the basic idea is, let's just think about one phase. We're not going to consider the 2 phase. Processor 0 creates, so what do you want to know? To send the data, forget everything, all the previous algorithm, and just say, I have this bunch of keys. Where should this key and its data go? What does it depend on? Well, it depends on if you can somehow find separator keys, that when the data is fully sorted, what is the separator between processor I and processor I plus 1. What key value is such that everything on processor I is smaller than it and everything on I plus 1 is larger than it. That's the separator for the ith processor, right? So if I can guess, if I can correctly compute the P minus 1 separator keys, the one between 0 and 1 and the one between 1 and 2 and so on, then I just need to do one data movement. How can I calculate such set of separators? Well, guess and check, right? So one idea is to just guess processor 0 then creates an initial separator keys, P minus 1, right? So the question becomes, how does it do that? What's a good way for 0 to create a P minus 1 separator keys? It can maybe sort its data and pick P minus 1, like if it has N over P, then it can pick N over P divided by P as the distance and say that one, that one, that one, that one, and it will get P minus 1 keys, right? And so you can just pick P minus 1 equally separated keys and say that's my separator. Everyone's distribution is same as mine, then it should work. But of course it's not. It won't be in the general case. But at least good initial guess. Now what do? Guess is not good enough. It needs to be tested. So then you broadcast that guess, the sets of probes, to everyone. Can you guess the remaining part of the algorithm? Anyone? You calculated some, you just sent to everyone some guess about what the separator key between processor I and I plus 1 for every I should be. That may be wrong or right. How do you find out? The answer is in the title, right? Histogram. So basically you just say, every processor looks at its data, maybe sort them ahead of time, let's say, and says, oh, you say separator between 0 and 1 is this key. Of my keys, that many, 793 keys belong to 0. By your thing, separator between 1 and 2 is such and such. Therefore, the next so many keys go into processor 1. So I can calculate a count of how many keys will go into each processor if we were to adhere to that particular distribution of that particular sets of separator keys, right? But that's, and so you can do then a global reduction across all processors to say what will be the global number distribution globally will look like for every processor if we were to use these separator keys. and that will be wrong. And then you'll say, okay, now can I adjust? The root looks at them and ponders. Well, the pondering is a little algebra. It just goes from 0 to 1, say, okay, that key on 0, not enough keys, I need to go a little bit to the right. And how far to the right I can go? I have the count for 1, so I know roughly how far I shouldn't go, and I just go somewhere in the middle. I make a new guess for in the middle of the range where I need to be based on the count for, let's say the count for bucket 0, the processor 0 separator was 10 million, whereas I wanted it to be 8 million. And so I look at the next processor's count using this. So then this count was, 10 million. So this means it needs to be smaller than that. And so I just take a value between my current separator and my leftmost point, and 4/5 of that, 20%, I say, okay, that's where I'm going to put the value. You can guess anything, doesn't matter. The numbers are not uniformly distributed necessarily. So therefore, trying to divide the value in the ratio of the proportion that we want is only a heuristic. It's only a guess. So you can guess some value in that range as the separator and keep doing that for every subsequent interval, and you get a new guess. So the new guess is guaranteed to be better than the old guess. All right? And you can broadcast that new guess to everyone, get the counts back, adjust the guess, keep repeating this until they are exactly equal. No, you don't really need to go to exactly equal. They are within 1%, or whatever your tolerance is, equal in terms of the size of the keys. Now you have the separators. Broadcast them to everyone saying, hey, this is the final one. And everyone says, okay, then my key, these keys go to 0, these keys go to 1, these keys I key because I'm 2, these keys go to 3, and so on. I just send them off once. So a repeated histogramming step for calculating the separators and adjusting them, and a single all-to-all phase is what this algorithm does. Is that clear? Does everyone understand how that works? Everyone calculates how many keys are there in each partition, reductions to bring, I'm just repeating the steps that I described. Reduction brings that to 0, 0 adjusts the keys and repeats the whole process of sending the keys to everyone. Everyone calculates a new histogram. How long does it take to calculate a to collect the histogram? You broadcast to everyone separators of size equal to P. If there are 10,000 processors, you broadcast an array of size 10,000. Okay, and then everyone takes their data, which is N over P, and loops over it, or doesn't have to loop over it, which is sorted. Does a binary search for each one of the keys, each one of the separators, and gets you the count for how many there are. So that will just be 8,000 multiplied by log N over P. Right? Because N over P is the size of the array you have. You don't even have to do a really full binary search. You will be in a range all the time. But worst case, N over P, log of that, that's how much checking you need to do to find the exact count for that key. And you do that count, and then you do a reduction of size P minus 1 again. Right? And so it's compared with the amount of data that you have, millions of keys, the size of the reduction is much smaller. And the number of times you have to do the reduction, if that can be small, then you are good. So then you will win with this algorithm. And in fact, a few 4, 5, 6 iterations of the histogramming are enough even for the really bad situations. But maybe really, really bad situations where the data is extremely lumpy. That is, there is lots of data in some regions of space and not much in others, and 0 made a really bad guess to begin with. You might need 10, 12 phases, but that's still not bad compared with the all-to-all movement, which you do only once. The data movement happens only once. So this was done by in 93 by Sanjeev Krishna, another one of my grad students, and then its optimized implementation was done in 2010 by Edgar Salamnik, who is a professor here now, and then more recently, one of my students just did, and it's not a published work yet, but improved this, and improved this in a couple of different ways. One is by using multiple cores on a node more effectively, and the other one was more theoretical. How did you calculate the initial processor 0 creates an initial separator keys. Can you think of a way of improving that? How can we make our initial guess to be as close to the real thing as possible? Yes? On your own processor, right? But your own processor ignores every. That's what I said here. The algorithm I gave you was sort my own data and then select equidistant p-1 keys. But it doesn't use information about how the distribution is on other processors. Yeah? But then everyone has p-1 keys, and then if you bring them all together, p square, that may not work well. You're kind of on the right track there. You want to somehow incorporate everyone's data. So maybe we'll come back to this question after we look at another algorithm, right? Let me look at this algorithm. Maybe it will give you some idea. So this is actually an older algorithm called regular sampling. So there are n keys on p processors, so everyone has n over p items. In phase 1, everyone sorts their own data, right? So I have my own data, I sort it, and now, again, if I have 10,000 keys and there are 10 processors, I need 9 separators, so I just kind of say 1,000th element, 2,000th element, 3,000th element, those are my separators. So I just equispace them there, so I'll get 9 separators. And so those keys that I find at those places are my separator keys. That's what I think they should be, kind of like what you said. And now we send them all to one processor. So I send my p-1 numbers to processor 0. You send your p-1 suggestions to 0. And 0 takes everyone's suggestions and its own suggestions, sorts them, and takes the every pth key, because now it has p square keys. So it takes every pth key and says that's the separator. And in fact, the sample sort, regular sampling sort algorithm said, just do that. Don't do anything more, just do that. And they didn't have the idea of histogramming in that algorithm. And so they just said, just do that, and you actually are guaranteed. This is, you can tell, there's a theoretician's algorithm, because you can actually prove that if you collect those samples, then, oh, by the way, so you send those separator keys to everyone. Everyone uses those to send it out to the right place. When it gets to the right place, you still have to sort it or merge it, and then you're done. So, so this one is also 1993, interestingly, and actually, I don't know if I want to go into the code just yet. 1 second. So in fact, it guarantees that if you do that, then the imbalance will be limited to 50%. That is to say, the worst loaded processor might have 3n over 2, 1.5 times n over p. Everyone is supposed to have n over p keys in the end, but it's possible with this algorithm that someone might have 1.5 times n over p keys. That means 50% more than they should, which is pretty bad, but at least it's some kind of a bound, right? Theoretically provable. In practice, it might be better than that. It might be pretty close to, within 10% or something like that. The worst case bound is 50%. So suppose I accept that. Do you see any other flaw with this algorithm? I'm running it on a parallel machine, Taub or something like that, maybe on 100 nodes, whatever, 24 cores each. That's one scenario. I'm running it on a machine with 1 million cores. That's another scenario, like 500,000 in case of blue waters. Yes?
Are we going to have the same problem where we're going to end up with
p-squared numbers on one processor? That is that a problem? Depends on how large is p, right? And so if p is 100,000, as it was on Blue Gene Q, which is a real machine, 100,000 nodes, each one with, even if you kind of say within node, I will just use OpenMP or something like that. 100,000 nodes, that will be like 100 square times a million, right? And so that's 10 billion keys coming to one node. You can deal with it probably, but barely so, and not on BlueGene Q. It didn't have that much memory. So p square is just too large a number to bring all into one place. That's one problem with this algorithm. But one can take the up to that point, this is good, and then the only problem is that it doesn't give you the perfect guess. But we know how to fix the perfect guess part. Histogram it. You don't have to take this initial guess that you get and accept it for what it is. And so that's what this new paper that my students working on did. It combines the histogramming and regular sampling and does it in a clever way and does it in a way that actually has provable properties. But basically, you don't bring all p keys from every processor. You sample a much smaller number. So, and there are proofs about how many you need to sample and so on. But let's say you sample something like 10 numbers from each node, right? And then that's a very small number of numbers. You bring them together and then you sort them, get the regular sample and say that's my initial histogram. Instead of doing it solely based on zeros distribution, you at least got some input from everyone else. Although very few numbers, as long as they're carefully randomly selected, you don't give the first 5 numbers or something. Give each one of your keys equal chance of being selected. Right, which you can easily do, but then just get small number of your keys sampled and build your initial histogram accordingly, send it to everyone, get the counts. When you get the count, what you do can again be another round of sampling. You could just do repeated histogramming at that point, but you can actually do a careful sampling within the ranges that you are supposed to narrow down the separators from. And by doing that clever trick, in a few rounds, with a small sample size, you can actually get a histogram accurately done. So that combines basically these two methods. So this thing here shows the code, which basically is worth looking at for you to see how to do this sample, how to express what I've been discussing so far into MPI codes, which is a skill you should learn. We don't have time for writing in constructing the code in the class, but it will be very good for you to actually do the exercise of writing the codes for yourselves, right? And even if you don't run them, at least check what it would look like. We're going to talk about a fourth algorithm for sorting, and the fourth algorithm is Quicksort. Sequentially, many people believe Quicksort is one of the fastest algorithms. What do you think? Do you like Quicksort? It's very powerful because it has a nice name. Quicksort. It must be fast. In fact, its worst case complexity is n square. So if you give Quicksort already sorted data and the algorithm is not carefully implemented, it can actually achieve that n square complexity, right? But carefully implemented variation of that can avoid that. But there is a sense in which Quicksort is still pretty good, and that sense is cache performance. It's an in-place sorting algorithm, and you usually go, remember the Quicksort? That one, hopefully you remember. You take 2 pointers at the 2 ends of the array or 2 ends of your region, and you move them towards each other. This side must be smaller, this time must be larger than the pivot. The pivot is just a value you pick randomly from the array, let's say typically from one end. Then you come from the other end and you say, oh, that's smaller than the pivot, that's okay, that's okay. That's larger than the pivot, that goes there in the vacancy that you created on the side. Then you start looping here and say, that's larger, oh, that's smaller than the pivot. It goes here in the vacancy this guy created, and the 2 pointers keep moving towards each other, and in the middle you put the pivot back into its place. So that's partitioning, and then you recursively sort each partition, right? So that's the Quicksort algorithm. Notice that you were nicely looping through the array backwards and forwards, right? And so your cache performance is pretty good. It's in place, unlike merge sort, which requires a separate array. Doesn't require any extra storage, so the memory footprint is small, and so overall its cache performance is pretty good. If you want to take that same idea and apply it in parallel, how would you do it? Your data is fully distributed across processors. You need to pick a pivot. Sequentially, you pick the pivot. How do you pick a pivot sequentially? you can pick it to be the first element, but just to get a little bit more, just like that sampling method, a chance of picking a number that's in the middle or closer to the middle, you can take 3 numbers randomly out of the array and take the median of those 3, and that at least has a higher chance of being closer to the middle. You don't want it partitioning itself into a very tiny part and a very large part, because that way lies kind of this n square complexity. So you pick a pivot in some fashion. Suppose you have picked the pivot somehow. You can take all your data, sort it, and take the midpoint, or you could sample from everyone and take a small sample and take the midpoint of that sample. You pick a pivot. What do you do after that? You want to know? In sequentially, using the pivot, you partition the data into the smaller array and the larger array, right? That's what you'd like to do. But the set of values that are smaller than the pivot may be only 20%, and the set of values that are larger than the pivot are 80% of all the data spread across all processors. That means after this, whichever way you do the partitioning, at the end of which you should only get 20% of your processors owning the smaller portion of the array and recurse on that, and 80% of your processors owning the remaining 80% of the data and recurse on that. That's what you'd like to do. How would you accomplish that? So you need to know how many are smaller and how many are larger, right? And so that's where you begin. I think I'm going to draw oh, this is not true. I'm going to skip that slide. Sequential algorithm you already know. I just described it. So I'm going to draw a picture. I was hoping to draw a picture on my slide so it remains there. Let's see if it's worthwhile. So you broadcast a pivot to everyone. Question is, how do you broadcast to everyone? You have a partition of processors. Do you make a communicator over it? You could make a communicator over it, but you're not going to do that many operations on it. You're just going to do one broadcast, maybe one reduction, and a few operations after that. But maybe useful to make that broadcast and reduction efficient. And then, so every processor partitions its data into 2 sets, smaller and larger. Make 2 vectors out of it, right? Or internally just separates them using the pivot into a smaller array and larger array. Now it knows how many there are, so we just have to count. You have to say the size of the smaller set and size of the larger set. So, and then let me just try to draw it here. If I fail to do that, then I will draw it on the board, and but at least for a couple minutes, let me try. Blank slide. Okay. So this is your set of processors, right? And each processor, which is, let's say, that is a processor going from there to there. Okay, fine. Let's just say that. And so it's a bunch of processors like that. Okay. And now what does this processor own? Whatever its data is, it's separated into whatever pivot value came from some node. I want to know how many of them are smaller, how many are larger. I just make 2 separate vectors of size, or within my own partition, I will logically draw them as separate vectors. Okay, I want color, but fill could be blue, orange and blue will do. Okay. Now that's a smaller set. Another processor has the same. Now, of course, the sizes of these may be different, right? So this might have fewer larger numbers than smaller numbers. So these are numbers that are smaller than the pivot, and their number is, let's say, S sub I, S0, right? And this is larger 0. And this is smaller 1, larger 1, smaller 2. I should ideally make subscripts, but no patience there. Larger 2, and so on. Okay. And so I need a sum of all the smaller numbers. So I can just write summation. I don't want that. That's not summation. Maybe much faster to get the actual symbol, but okay, forget that. Sum. S0, S1, S2, S3, the summation of all Si will give me the total number of small numbers that I have. And summation of Li will give me the total number of large numbers that I have, smaller than the pivot and larger than the pivot, right? And so I can do that reduction. Just the count, 2 numbers contributed from everyone, so I can make an array of size 2, do the sum reduction, and now at the root processor, I know that there are, 73 million smaller numbers that are smaller than the pivot, and I had to pick that. Okay, fine. And 27 million numbers that are smaller than the pivot. I only have 10 processors, and so I'm going to send 10 processors, 7 of them to do the smaller part, and 3 of them to do the larger part. Slightly unequal, but hey, that's all I can do. And so, and then now, one set of processors says, okay, but now you have to redistribute the data. How do you redistribute the data from everyone's larger part? This guy is L0, but the larger partition begins somewhere here on processor 8. So I need to send it to 8. I need to send to 8. I need to send to 8 or 9 or 10. Where should my data go? And this turns out to be exactly the same problem that we solved with prefix sum of data balancing. Remember, except that the data is going not to the same sets of processors, it's going to a subset of processors. So you can just do a prefix sum of all these SIs and LIs, and knowing the total, knowing which processor to begin with, based on the prefix sum, that is, I know I'm on one of these processors here, I know there are these many large numbers on my left. How do I know? Because the prefix sum told me that there are that many large numbers. Therefore, my data needs to go to that and that other processor on the right side. Similarly, I know my small data, there are so many on my left side, therefore it needs to go to this and this processor. I can calculate that just like go back to your algorithm for data balancing using prefix sum, and you can just apply it and I just send the data to the right place and I'm done. Well, not quite. I'm going to be sending my data to 3, 2, 4 other processors. Why? Because I have contiguous data, right? All my data is in some kind of a the prefix sum tells me it's not sorted, but I have the data that I need to send to only those processors according to the prefix sum algorithm, right? And so it is just going to tell me this data needs to go, the data that you own needs to go to processor 14, 15, and 16, right? Maybe not too much more than that, because if I originally did not own a huge amount of data, then half of my data cannot go to more to like 20 other processors, knowing that they themselves need to be n over p anyways on the average. So it will go to a small number of processors, typically 2 to 4. How do you know exactly how many to expect? So that the receiving processor can say, oh, I'm going to issue a receive for 3 messages because I'm going to get 3. How does it know it's going to get 3? Maybe there is a 4th one sending to it, or maybe there are only 2. If you're doing this in Charm, you could use quiescence detection. You could just send the messages, wait for something called quiescence to happen, and then continue the execution after that. If you're doing an MPI, you need to do something like a separate all-to-all type operation. You'll have to do a all reduce, basically, followed by a scanner, which basically says how many messages I'm going to send to 0, how many I'm going to send to 1, how many I'm going to send to 2. Most of those are 0 except for 3, 4, 2 processors in the middle, and you do a reduction of that, and now every processor knows that I will be getting 3 messages, because the sum from everyone told me that I'm sending 1 to you, 1 to you, 1 to you. Someone else said I'm sending 1 to you, 1 to you, 1 to you. That's only 2, and so I'm going to get 2 messages on my processor, right? So by doing an all-to-all reduction as a simple operation, we can think about other collectives there. You can find that count. It's an unnecessarily expensive operation, but that's one way of doing it. You could also just send, you can do variations of that collective algorithm. We'll talk about it maybe later when you do the collective algorithms. So once you know that, you get the data, and now you have the quicksort phase 1 done. Recursively, you recurse, but notice that you recurse on unequal partitions. Every time I need to know what is my min processor number, what is my max processor number, what is the N over P that I'm trying to get to, well, what is the total number of total size I've got across all of them, and then I can recurse, right? Just all the data that I got from everyone, I merge it into one vector and combine, concatenate, not merge in the sense of sorting. I just put that together, and then I'm ready for the next phase of the algorithm. Once it comes down to my range is min processor number and max processor number of the same processor, that means I'm talking about just one processor. That means I can do my work myself, no communication needed. I can just sort the data that I have. All right, that's the end of the recursion. At every other phase, you'll be redistributing the data. So what's nice about this algorithm is that it implements our quicksort that we are all familiar with and love and care about. Okay, but what's bad about this algorithm is that, yes, what's bad about this algorithm compared with the previous 3 that we looked at? How many times does each piece of data move? On the average, if you had reasonably well behaved recursion, as many as there are quicksort phases going down, right? And there will be log P quicksort phases. So you'll divide the sets of processors, 1000 processors into 500 and 500. For that, you will do an all-to-all like operation, right? This data will move. Half of your data will move to the other partition. The other half will move to your partition, but presumably to some other processors, so as to keep the load equal. And then you do that on 500 processors, where again your data will move once to the other partition, and now you're back to 250 partition, where your data will again move. All your data will move. Most of your data will move, and that goes on all the way down to 2. So log of 1000 is 10. So log P phases, and every phase the data moves once typically. And so data movement is huge here compared with any one of the previous algorithms. For the Radix sort, the data moved 4 times with the 64-bit key. For histogram sort, it moved once, assuming you don't do multiple phases in that. And with this, sample sort, it moves once, but it had the problem of p-square memory on one processor and not adequate guarantee of good load balance. And then this algorithm moves the data too many times, log P times. So quicksort is not a very practical algorithm, but it's an interesting algorithm to see how to do. Like its use of prefix sum and so on actually are good training material for understanding how to use MPI for doing whatever it is that you want to do effectively. Right? Okay, we'll stop with that.